Welcome! In this video, Ken K3YEE talks antenna basics.
All right, the basic vertical antenna. What's vertical? You got two people with a jump rope. If you shake it this way and create a standing wave, you've created vertically polarized wave, okay? Simple way to understand vertically polarized wave. So the basic vertical antenna is a quarter wave length over a perfect ground, infinite, perfectly conducting. And that's not earth, meaning dirt. Dirt is a very poor conductor. Seawater is pretty good. But if you don't, otherwise, you know, if you don't have a sheet of copper, even aluminum was, you know, will do, you don't have an ideal dipole. And you also probably don't have a, quote, infinite ground. Okay, the current in a dipole from the base to the tip is a quarter sine wave. It's maximum at the base. It's zero at the tip because there's no more wire. There can't be any more current flow. Okay? And conversely, the voltage is a minimum or near zero at the base and is a maximum at the tip. Don't touch the tip of transmitting antennas. Even with 5 watts, you can feel them.
Yep.
And, okay, all right, if you don't have this ideal ground plane, well, they say you need radials that are a quarter wavelength long, and you need 8, but 16 is better, or more is better. In order to, you know, if you're at ground level, in order to simulate that ideal ground plane. However, if you're elevated above earth ground, this is a so-called ground plane antenna, a 2-meter ground plane antenna, which is my special fold-up one. Well, this tells me that if you're elevated, and what's elevated? Well, a couple wavelengths maybe. That four radials is enough. And well, why is it bent down? Because the dipole is something like 37 ohms. And most of us want to drive it with 50 ohm cable. Bending the radials down makes it closer to a 50 ohm match. Okay? So since I'm making my own, I now have 3 radials. My own plug was, well, this is a quarter wave, 2-meter, and it happens to be obviously dual panned dipole. So it has a coil in the middle. So for 2 meters, it's This is a loaded quarter wave. Well, what happens to the loading? This was our current. Well, that loading coil kind of takes out a little section in the middle, and it is not really radiating the same as the full dipole would. And the coil acts though as a high impedance at 440, so that the bottom, so that this looks like a block, so that the bottom part resonates at 70 centimeters. Now, if the designer of this was really smart, he's made it though so that the top part also radiates at 70 centimeters, and this would then be a collinear vertical for 440, but it's a center-loaded quarter wave for 2 meters. If you're 11 meters, quarter wave's 102 inches, but the one on your car was, you know, typically 3 feet or 4 feet, and it had a humongous loading coil at the bottom. Well, what's bad about that? Remember, this is the base. It was throwing away all of the high current part of the base of the antenna, and radiating, you know, from the last 1/3 or something of the, or 1/4 of the total length. So base loaded antennas are, you know, are not desirable, but 11 meters, they were very common. Well, to plug my invention, to make this mag mount have a ground plane, I invented the can lid with 4 radials that are 1 meter across in order to provide the ground plane. Just incidentally, if this is a 5/8 wave, which I'll talk about in a second, instead of 1 meter across, I read that it needs to be, I'm switching units, 42 inches instead of 39.37 inches. Okay, but this simple way to put, if you want to turn your mag mount into an antenna that can be put, you can put this anywhere. So you can hang it from a tree. And if anybody wants to build one of those, I've got some extra can lids. Okay, let me see. Otherwise, you know, people talk about putting their mag mount on a pizza pan, but you need a 1 meter diameter pizza pan in order to have the correct ground plane. And I don't think very many people have, you know, 1 meter diameter pizza pans. The radiation pattern now of that quarter wave is approximately like this. There's 0 radiation off the tip, and obviously there's no radiation into the ground, and the radiation is omnidirectional, and this is you know, is bulged out. Well, it's not. The bulge is so the radiation pattern looks, you know, something like this, if you're slicing it this way. Okay, and it has a maximum in some direction, which is about 27 degrees for this quarter wave ideal dipole, and relative to the isotropic radiator, it is okay. But this is the quarter wave. It's 0 dBd and 27 degrees. Okay. All right, so what about other length antennas than the quarter wave? The next, commonly used one is a half wave, and the current in the half wave, from the base to the tip, is going to be a half a sine wave. It's the current zero at one end, and it's also zero at the other. And likewise, now the voltage of the half wave, though, it's high at the base, it's high at the tip, and it's near zero in the center. And of course, it's going to be the same when we talk about a half-wave dipole a little bit later. It takes, though, to drive. There's nothing. This is nothing. If it wasn't loaded, this would be nothing but a 19.5 approximately inch piece of wire. There's nothing in the base of a quarter wave dipole valve. But this is a half wave that happens to be, center loaded dual band, and there's some magic in here, because in order to drive it, it takes a high voltage at the end in order to drive an end-fed half wave antenna. Well, what's in here? Well, it could be the matching coil may look like this, which is what's known as an auto transformer, and it'll have a step-up ratio in order to generate the high voltage in order to drive the end. And again, this happens to be a dual band, and you can't tell whether this is a 5/8 wave or a half wave by looking at it. So, you got to read the specs for the model in order to know. Now, a half wave will operate without a ground plane, but it has more gain if you're using it as vertical. It has more gain with a ground plane. So a half wave in DBD, it's got 1.6 DDD and 19 degrees, so that, okay, the quarter wave was radiating at 27 degrees, but the half wave, the maximum radiation, is 19 degrees. So it's putting more down lower instead of heating up the birds. Okay. So then. The next commonly used one is a 5/8 wave. This is a 5/8 wave, 2 meter only. So this is a full 5/8 wave at 2 meters. And I have a quarter wave on my car because it's the only thing that'll clear this garage. And I don't recommend this on top of your car you know, in this garage, if you don't have a fold-over, you know, antenna mount. Now, there's got to be, again, a magic matching coil in order to drive this 5/8 wave. And the current has to be, you know, this is the halfway, which is 4/8, but there's got to be there's got to be another eighth of a wavelength over here somehow, and I could not find any reference that told me what the design of that base coil is in order to drive this 5/8 wave, but it takes, you know, a magic matching coil in order to drive a 5/8 wave. But 5/8 wave is 3 dBd. And the angle now is down to 16 degrees, which is, you know, we're getting down to this level. So you're putting, you know, more radiation in the direction, you know, that down low, right? Well, I don't want to go into the details until later, but there's antenna that I talked about at Show and Tell last year, which is a halfway. Well, it's a slim. It's called a Slim Jim. And it's a halfway modified J-pole. I'm going to talk about it at the end if I have time. But the reason I want to put it up here is its radiation is down to 8 degrees, which is getting pretty low. And it's become known as Aleksandra antenna because that's what I was built, and it was the only thing that she could hit the repeater with from inside her house. It has, it has the potential for twice the gain of a half wave, but I'll talk about it later. Okay. All right. I'm not going to talk about HF verticals because, you know, if you want to build this, you know, an HF antenna for 80 meters, you know, it's 66 feet high, and those radials have got to be 66 feet long, and I don't think too many people are going to put up 80-meter verticals in their, you know, backyard. And there are many, you know, commercial multi-band verticals that are all proprietary designs and quote, magic in order to resonate on the ham bands without, and most of them, you know, don't require those 16 radials or whatever underneath them. Some of them have little short radials at the base. Some of them may require, you know, you to put out a radial field. But if that's what you want, they are used for DX because they have lower angles of radiation than the dipoles, which we're going to talk about next. Right, we're going to talk about now horizontal. Horizontally polarized antennas. You in the jump rope, we now would shake it this way and create a standing wave. So that would be a horizontally polarized waveform. very simple to visualize if you ever play jump rope. So obviously the basic horizontal antenna is a half wavelength dipole in free space. What's free space? And actually, I don't know, but I'm assuming it's several wavelengths above Earth in order for there not to be ground reflections that affect the half-wave dipole. So the half-wave dipole has a radiation pattern that looks like this. There's no radiation off the ends. It's a donut in this direction if it's in free space. But as soon as you get it anywhere near Earth, that starts getting distorted. And and first of all, now this actually looks like something like 72 ohms, but everybody drives them with 50 ohm coax, but it's not really the right match. Right, the half wavelength, at 80 meters, is something like 133 feet for the dipole, which means that, if you now have real Earth, if you're not significantly higher than a half a wavelength, you have what's called an NVIS antenna, which they want to test a, what is it? Shirley, which is intentionally an NVIS antenna. Well, what does that mean? That means that this dipole, instead of looking like this, has been distorted, so it kind of looks like this. There's no radiation, but it's bulged up because of the ground reflections. And I found since this is a dipole, it obviously it obviously has a gain of 0 dBd if it's in free space, because that's what it references. And the current's going to be that half sine wave, and the voltage is going to be high on the tips and near zero at the drive point. Again, you don't want to touch the ends of a transmitting dipole. All right, I found that if you're up 1/3 of a wavelength, this is a half wavelength, so that in order to be up, anyway, if you're up 1/3 of a wavelength, I found that that the radiation maximum is now up to is up at 54 degrees. In free space, the maximum is horizontal, and if you're closer to ground yet, it's going to put even more straight up. Okay. well, if you can't put a dipole, you know, a half meter or a half wavelength or more above the ground, you know, you do what you can. You put it up as an inverted V. And if you can't even do that, if you have to, you know, fold the ends down. If you fold 20%, remember the current looked like this. So it's the low current ends that you're messing with, and you know, so you're not losing that much because the maximum radiation is where the current is highest in the center. So, you know, if you can't put it up 100 feet high, you know, do what you have to. You're the one that didn't have a big enough lot for a 102-foot dipole. You know, in fact, you know, even if you know, do whatever you got to do in order to fit it in your, you know, for going 90 degrees to fit it in your lot. Okay. This is a 2-meter dipole, and the magic way I adjust the length is just by twisting it back. And as I said, I've never built one of these to the calculated length without having to adjust it, and I'll talk about it at the end a little bit about how you know how we adjust it. This happens to be a vertical dipole for 2 meters, which I use hanging in the window behind my HF rig to work the repeater. However, you have to run the feed line at least a quarter wavelength perpendicular to the vertical dipole in order not to detune it. So, but the vertical dipole is much easier to build than a J-pole, which I said I'll talk to later, you know, as an alternative half-wave dipole. It's just much easier to build a simple dipole than to build something like a J-pole and to tune it. And the reason I would mention that is I also use a 6-meter vertical dipole that hangs from the edge of my roof down to my deck rail, and I can hit it from down near the main site with 5 watts. Well, that's not that important now, but back before we went to digital TV, if you operated 6 meters, you caused TVI to your neighbor on channel 4, which I guess that problem's gone away since we've moved off of channel 4 and channel 2, you know, into the digital world. But my point is that you lose 20 dB if you're cross-polarized. If you try to hit a repeater with a horizontal antenna, it's going to take a lot more power in order than if you have it correctly polarized. So I can hit the repeater with 5 watts with the vertical, but it might have taken me 20 watts, you know, with the horizontal dipole. And I said, at the time I put that up, my neighbor would not have liked, even if he had cable, probably, you know, that might have caused interference. Okay, you know, dipoles. Dipole is nice, but it only works for one frequency, and most people, you know, want a multi-band HF antenna. So how do you make, you know, multi-band HF antennas? Well, it's very easy. One way is you just add more dipoles. And you can easily make a fan dipole that works on 80, 40, and 20. And you can buy one of these if you look in the back of QST, but they typically have some kind of mechanical spacers in order to keep the fan open. But believe it or not, if you're on 40, the fact that the 80 and 20 dipoles are there, it doesn't really affect it that much. So this is one way of making, a multi-band horizontal antenna. Right, the other. Other way is what's called a trap antenna. Same thing over here. This is an inductor in parallel with a capacitor, which is a resonant circuit. At the frequency of resonance, a resonant circuit has a high impedance. So when this is resonant, this looks like a block to that first section of wire. So just that first section is active. It doesn't even see what's beyond it. So then at a lower frequency, this one is resonant, and this is not resonant, so it becomes a partial loading coil. So now you've got this section that's another band, and then at some other lower frequency, the entire length. So this is a tri-band dipole with traps. And you can make traps, you can buy traps, you can probably buy a trap dipole, again, 40, 80, and 20 or something, or actually they probably make trap dipoles that are just higher bands, Okay, there's another simple way of operating well, I didn't say, but I was presuming that we've been talking about driving dipoles with 50 ohm coax. But if you put up that 133 foot 80 meter dipole and you drive it with 450 ohm ladder line or 600 ohm open line, but then you're going to need a ballad to convert from balanced lines to coax. But then you're going to need a tuner. This is going to be code, and then your transmitter. All right, well, what's the ballad? The ballad could look just like a transformer. That's a voltage ballad. It could look like this, which is the current ballad. But anyway, it allows you to, it converts from the parallel line to the coax. Well, what's a tuner? Tuner might look like this. have two variable capacitors, a Ci and Co, and a variable inductor. And this is the transmitter, and that's the antenna. And you magically turn all three of them at once for minimum SWR to match. So you can use this 80-meter dipole now on everything up. People tune it up to 6. But you got to remember that you're going to have, you're going to have, at higher frequencies, you're going to have multiple wavelengths, that are resonant. I mean, you can tune it up, and okay, let me ask, I got to ask one more question. Why you got to use ladder line? Why not coax? Well, at the higher frequencies, the SWR could be anything from 1 to 20 because it's mismatched, except at 80 meters. And SWR, that means the peak to valley, could be 10 or 20 to 1. Well, why is that bad with coax? Because the loss in coax goes up significantly for high SWRs. You have, because of the peaks in the current due to the SWR, you have more resistive loss, and you also have more loss in the dielectric that you're just heating up. If for example, at 10 megahertz, if you have 100 feet of coax, crummy, good old common RG58. The match loss is 1.5 dB, just because of the resistance in the wire and whatever. But with a 10 to 1 SWR, you got two more dB loss. So now we got more than 3 dB, and we've got half our power that's doing nothing but heating up the wire. Conversely, if you use open or ladder, I'm told that the whole combination, including the SWR loss, could be a half a dB in comparison. So this is one way of having an all-band antenna, except at the cost of having a ballad and a tuner, which may come together. I mean, I have a MFJ, whatever, legal limit tuner, and it has a 4-to-1 ballad in it. So 4-to-1 is 50 to 200 ohms, is not really matching the 450 either. But remember, the tuner doesn't do anything except make a standing wave ratio of 1-to-1 down here. It doesn't do anything up here. If it's 20 up here, it's still 20, but it makes it so your transmitter sees 1. And believe it or not, if you have a match even though you got that SWR and things bouncing around, all the power gets radiated. I mean, the conservation of energy, it has to go someplace, and believe it or not, it gets radiated if you are able to tune it up. Okay, so and that happens to be the kind of antenna that I have in my backyard. It's up about 60 feet, and it's a inverted V, and one of the ends has got 20 feet that bends 90 degrees because my neighbor didn't have a tree in the right place. But again, I say, in practice, you do what you have to do, and